Can you hear it? Okay, good. All right, let's get started. So let's start with a model that most of the people here knows. So this is, because I come from the background of non-equilibrium statistical mechanics, so this is a model that I always work with and always begin with. So this is the so-called larger one Cramer's equations. It's a SDE model describing the positions x and the velocity v of a free particle. So free in the sense that there's no external force acting on a particle, and an equilibrium heat bath. Oops. All right. So in the second equations for the velocity, you see that there's a damping term, and then there's this damping coefficients gamma and the noise term. Here is a white noise term with noise intensity sigma. And because this is an equilibrium heat bath, the Einstein relations hold. So it means that the noise coefficient sigma is related to gamma as follows. So, thank you. It's okay. Yeah, thank you. All right. So this is a model that I hope most of the people here are familiar with. Now, let's consider two cases in mind. The first case is when both of these damping constant and noise constant are, coefficients are constants. And the second case is when both of them are dependent on state. So it means that they depend on the positions. So keeping in mind these two cases, now let's ask the following questions. Because usually it's justifiable to take the limit as the mass goes to 0. This is usually justified when there exists wide separation of time scales. And in the community of statistical mechanics, this is often referred to the over-damped limit. So, so let's consider the problem of taking this singular limit and ask what should be the limiting equations in the considered limits. So remember, just now we considered two cases, right? The case when gamma and sigma are constants, and the other case when they could depend on the state. So, well, a naive procedure, which might be a bit too simple, right? Just to say, simply set the mass equal to 0 in the equations for the velocity, rearrange the terms, and then you get the limiting equations, which is nothing but a linear process with scale coefficients, noise coefficients of sigma or gamma, right? But so now, is this true for both cases? So this is worth thinking about, and the answer is, as you can guess, it's true for the first case, but not for the second case when they depend on the state. So a closer look at this is that we need to understand what we meant by stochastic differential equations. So this goes to the basic again. So we write down the integral form of the equations, and after integration by parts, you can isolate terms like momentum, mv, and kinetic energy, mv squared. It's boxed there. And using Ito calculus, you can compute the second moment of the moment. The momentum is like order of m, as m goes 0. So you expect the kinetic energy, mv squared, is like order 1 in the small mass limits. In fact, here, x is a slow variable and v is a fast variable that homogenize in the limits. Physically, you can derive this easily because, so remember that we are in the situations of equilibrium heat bath. So then there's this equipartition theorem that tells us that equilibrium kinetic energy is on average equal to the thermal energy. And this can be, so then from this we can get mv squared. We should expect mv squared to be sigma squared over gamma. And then this should be the correct limiting equations. So far I just said this heuristically, no justifications, but there's an underlying theorem that where you can prove rigorously these convergent results. And more, just to build some intuitions, what happened right, in the limit as the mass goes 0. So if we plot the trajectory of the positions, you see that when the value of the mass is large, you get a rather regular trajectory. And if you decrease the mass to, let's say, mass m equal to 10, you see that the trajectory becomes rougher. And if you decrease some more further, it becomes rougher. So it gets rougher and rougher. And in fact, if you look at the limiting equations there, there's a so-called noise-induced drift. So this term is coined because if you simply set mass equal to 0 in the original equations, you won't get these equations. So this is sort of like a correction terms to the limiting equations. And interestingly, if gamma is a constant, the noise-induced drift vanish. So in the second case, when both gamma, well, in fact, you just need gamma to be dependent on the state, you always have a non-trivial noise-induced drift terms there. And in fact, this correction terms has been observed experimentally in the experiment of Brownian particle near a wall, where the diffusion constant depends on state. So it depends from the distance from the wall. So anyway, so far everything has been rather simple and built on some intuitions. And now the real thing about the talk is generalized algebra equations. So as you can see from the title, generalized, meaning that we are going to generalize the equations that we saw just now to include more interesting effects. So if you look at the equations in the equations for V, you have now not only instantaneous damping term, but also a non-instantaneous damping term involving an integral over the memory kernel, right there, and also it depends on the path velocity. And the noise is now not only white noise, but here we generalize it to be a color multiplicative noise. And you can think of it as some general model, right, for a particle interacting with a heat bath. And of course, because we are here in this school for climate and the environment, you can think of this particle as a climate and the noise, the heat bath, as weather, small-scale processes. And so in fact, here I also assume that the noise CET is a zero mean stationary Gaussian process. So it means that then the statistical properties of it is completely determined by its covariant functions. And also we can look at the Fourier transform, the so-called spectral density. And here in these formulations, everything is pretty general. So you see there are many coefficients there, gamma 0, sigma 0, G, H, sigma. These are very general and they are not necessarily related to each other. But of course, there are special cases in statistical mechanics, right, when fluctuation dissipation relations hold. Then this model can actually be derived from a microscopic Hamiltonian model or from the famous Morrizonzi formalism. And in fact, this Morrizonzi formalism has been used recently to derive some delay differential equations in climate science. Anyway, so these are all the possibilities for the applications. So the focus of this talk is really on how to reduce a model in a meaningful way while keeping the essential information about the original dynamics. And remember, in the Langevin-Kremers case, right, there's a time scale associated with the mass, the initial time scale. But now for the generalized system here, we have more than one time scales. This is also more realistic from modeling point of view, right? Because usually there are multi-time scale in the system. And because this is only a short talk, so I'm just going to focus on two special examples. And this is a special cases of a much more general result that we have. So for the first one, let's consider the following one-dimensional model. So here, the position and the velocity is one-dimensional. And we throw away the instantaneous damping and the white noise term. So here you only have the color noise term in the equation 6 and the memory term here in the middle. So for the first model, let's consider the memory functions or memory kernel to be a difference of two exponentials with two different decay rates. Okay, so gamma 2 and gamma 1 there. And then you can, the Fourier transform of this function is simply Lorentzian like this. So let's ask the following question, I also want to mention the second model. So the second model, model 2, is simply a special case of model 1, where you send one of the decay rate, gamma 2, to infinity. And then the memory functions become something like this. And the important features for both of these models is that the spectral density, right, of the noise scale as omega square, right, at low omega. So in this case, at least in the case of when you have free particle and when GH sigma, they are all constants, you can show that the mean square displacements of the particle is scales like t square as t goes to infinity. So this is actually providing us a model for anomalous diffusions. And in fact, because it's t square, it's ballistic diffusion. So remember, we want to do model reduction, okay? So let's consider the first case where we only send the mass to 0. And then we should expect to get some reduced order equations. And in this case, because we allow the coefficients to be state dependent, so we should also expect that there will be noise-induced drifts. And in fact, it's true. And as you can see, again, under some assumptions on the original equations, you can prove that in the limit as mass goes 0, you can get the following equations for the positions. And now you see that it's not so trivial as before, right? As the Langevin-Kremers case that I told you earlier. Because here in the equations for x, it's coupled to equations for other auxiliary process. And more importantly, the noise is no longer white. It's a no-Markov process. Okay? Usually in the model reduction business, people always want to take white noise limits and simplify things further. But here, for this case, for the anomalous diffusion model, you see no Markov effect in the limit. And so let's just forget about this because we don't have time, but basically this is a special case. So for the second example, what if we send both the mass, so here I rescale the mass with epsilon, and also rescale the gamma 2. So remember gamma 2 is one of the damping rate of the memory functions. So what if we send both mass and gamma 2, so send mass to 0 and gamma 2 to infinity. So this corresponds to sending both initial timescale and part of the memory timescale to 0 at the same rate. And if you do this, again, you can prove this. I'm not going to show the detail, but then you will get the following result. I will come back to this. So again, it looks not so trivial compared to the Langevin-Kremers case. And if you compare with the first example, you see that the noise-induced drift here, so it's highlighted in blue here, is much more complicated. And in fact, you can make some observations. Skip this. So let's look at the 4, right? The fourth point. In fact, the limit of sending first gamma 2 to infinity and then taking mass to go to 0, the result is not the same as taking the joint limit of mass and gamma 2, okay? So now let's go back to this here. So why are we taking limit in this way, right? So again, this model is a model for anomalous diffusions. And if you scale the parameters in this way in the model, as epsilon goes 0, you can see, so this is a graph of the memory functions, okay? So if you take gamma 2 to infinity, right, so if you increase gamma 2, you see that the environment somehow allows for more and more negative correlations. So this preserves some non-trivial informations from the environment or the small-scale processes in terms of climate modeling. And so we want to retain these informations in the reduced model. Let's go back. And of course, in the special case when G is proportional to sigma, or even in the even more special case when you have fluctuation dissipation relations, these two limits actually is the same. But as Varela Lucarini just remarked earlier, processes in climate are usually out of equilibrium. So we should expect these two limits will give us different result. All right, so now let's just briefly summarize what we have talked about. So in this talk, we'll talk about new kind of homogenizations or model reductions for generalized version of larger one equations. And the key message here is that the reduced model retain non-trivial effects from the memory and the color noise because of the way we take the limits. And it's very important because we want to preserve some essential information about the original model. And of course, you will get simpler model when you impose some statistical relations, such as the frustration-dissipation relations. And this, I guess, has some implications for climate modeling here. And if you want to know more about technical details, the conversion result, basically, you can look at the first paper. And also here, I list down some other related papers. So I also put down the last paper there, which is not really related to homogenizations, but it's a project that we are currently doing to use machine learning to predict rare events in multi-scale dynamical systems. So basically, we do this in the framework of deterministic homogenizations, as opposed to the stochastic homogenization here. Thank you for your patience.
Thank you for keeping the time and the nice presentation. Perhaps time for a question.
Oh, yeah, thanks.
You mentioned something about stochastic homogenization. In this approach, you use the deterministic formulation. What do you think would happen if you adopted a stochastic formulation?
No, because the thing is, depends on the context of the problem that we're after. Because for this last paper here, we are studying a bistable system driven by a fast Lorentz 63 systems. And you know, if you rescale the Lorentz system appropriately in the limit of the epsilon, the scaling parameter goes 0, it goes to a white noise in the weak sense, right? So we are studying basically focusing on this bistable system driven by the Lorentz 63 systems because we think that this is a good starting point to apply this machine learning framework to predict rare events for these bistable systems, which is of course of relevant in climate science community. Yeah.
Okay, thanks.
Any more questions? Well, if not, then we are over time anyway. So I would like to thank for your participation, everyone, and most importantly, thank you again, all the speakers.